The official story is that Roman engineers built the foundation for the temple at Baalbek. Look at the three largest stones. They weigh 800 tons each. Be honest, a modern heavy lift crane, one of the biggest in the world, avoids a load like that. It takes weeks to assemble on a reinforced concrete pad just to make the attempt. But the real problem isn't the weight, it's the silence. The Romans documented everything, from aqueducts to battlefield surgery. The simplest check is to read their own engineering manuals. They brag about far smaller projects. Their complete silence on Baalbek is a confession. This video is not about how they lifted the stones. It's about why this foundation exists at all. It sits on solid bedrock, making it the most over-engineered, unnecessary structure in the ancient world. By the end, you'll see Baalbek not as a temple, but as a crime scene, where the real mystery is a vanished logic that made this impossible platform necessary. The cross-examination starts now. The official purpose of the foundation was to support the Temple of Jupiter, but geological surveys of the Bekaa Valley confirmed the temple sits on solid bedrock, ground that needs no heroic reinforcement. Look, this is like building a nuclear bunker to support a garden shed. Any practitioner fits the solution to the problem. Here, the solution is absurdly bigger than the problem it supposedly solves. The Romans themselves invented waterproof concrete specifically to avoid this kind of insane labor. That was their signature move. You cannot cheat the builder's own logic. Why would the masters of efficiency choose the single most inefficient method to solve a problem that never existed? An 800-ton block is not just heavy, it's a logistical singularity, the weight of several jumbo jets. To move one today, a specialized crawler crane is required, a machine so large it ships in pieces on dozens of trucks. Check the spec sheets for any modern heavy lift crane. The ground pressure requirements alone demand a purpose-built road or pad. Think. The area around Baalbek is ancient ruins, not a modern paved construction site. The ground itself had to be prepared to support the very machines that would move the blocks. That preparation work would leave its own massive footprint. Where is the evidence of the reinforced causeway needed to support the lifting equipment? And it gets worse. In 2014, an even larger block was found still in the quarry, weighing an estimated 1,650 tons. Be honest. This isn't an anomaly. It's a declaration of intent. The builders were not just capable of moving 800-ton objects, they were actively working towards moving things twice that size. This abandoned megalith, sometimes called the Stone of the Pregnant Woman, lies at an angle, fully carved but never detached from the bedrock. It captures the exact moment the project stopped. Do the simplest check. Analyze the tooling marks and the state of the stone. It wasn't a failure of quarrying, it was an abandonment of the entire project. What kind of event is so sudden and absolute that it forces a civilization to walk away from a multi-generational project of this magnitude, leaving their single greatest achievement half-born in the rock? Let's start the cross-examination at the point of physical contact. The three Trilithon blocks are not just heavy, they are precise. The fit between these 800-ton stones is so exact, a knife blade cannot be inserted into the joints. A feeler gauge slid along the seams today confirms near-perfect contact. With modern laser-guided cutting and computer-controlled placement, this would be a monumental challenge. With ancient tools, it seems impossible. Think. You are not just lifting and dropping. You are mating two massive surfaces with near-perfect alignment on three different axes. The slightest error, a tilt of a fraction of a degree, and the block either jams or leaves a visible gap. What was the measurement and feedback system that allowed for real-time corrections? The problem of precision is compounded by the material itself. These are not uniform blocks of cast concrete. They are hewn limestone. Any quarryman will tell you that stone fractures unpredictably. To get 3 blocks of this size with perfectly flat, true faces suggests an incredible mastery over the material, or a staggering amount of waste. For every successful block, how many were ruined by an unseen fissure or a mistake in the final dressing? The quarry itself should be littered with giant failed attempts. Some unfinished blocks exist, but the sheer volume of waste rock required to produce such perfect monoliths seems unaccountably small. You cannot cheat the nature of the material. What was their rejection rate, and where did all the colossal failures go? Now, consider the placement. The Trilithon stones are set on a course of smaller, but still enormous, blocks below them. They form part of a retaining wall on the western side of the platform. This means they were lifted and maneuvered into a specific position in a wall with other massive stones, both below and beside them. This is not an open field lift. It's a tight, constrained assembly process. Any modern crane operator will tell you that lifts in confined spaces are exponentially more complex and dangerous. The available space for machinery, for pulling teams, for counterweights, shrinks to almost nothing. Walk the site and measure the clearance. A narrow service gap exists between the megalithic platform and the later Roman structure, showing they were built independently. This gap is too narrow for any conceivable large-scale machinery to have operated. So, if the machines weren't in the gap, where were they? The stones themselves hold another clue. Standard Roman lifting techniques involved cutting holes or leaving protruding bosses on the blocks for their cranes and levers to attach to. These marks are a standard, practical solution, visible on Roman blocks all over the world. It is their signature. Look, the Trilithon stones have smooth faces. There are no holes for hooks, no bosses for clamps. So how were they gripped? The force required to move 800 tons through friction alone is immense. Any ropes or harnesses would need to be impossibly strong and would likely damage the sharp, precise edges of the stone. This detail is not minor. It's a direct contradiction of known, documented Roman methods. Reality does not care about your story. If you cannot grip the stone, how can you possibly move the stone? Let's talk about the money. A project of this magnitude would have a budget comparable to a modern aircraft carrier. Who paid for this? It would require a state-level actor with immense resources and a compelling reason. The official narrative suggests the Romans did it for a temple to Jupiter. But the temple itself, while large, is dwarfed by the engineering effort of its own foundation. Any project manager will tell you the cost of this platform would have exceeded the cost of the temple on top by an order of magnitude. It is like building a mountain of solid steel just to support a flagpole. You allocate resources to the visible, high-impact parts, the columns, the statues, the grand entrance. Here, the vast majority of the budget and effort was sunk into a foundation that was largely hidden from public view. Why would any sane empire spend a fortune on the part no one would ever see? Think about the return on investment. A Roman emperor would authorize such an expense for glory, for political stability, or for a clear, functional purpose. The glory of the Trilithon was invisible, as it was part of a retaining wall. Its function as a foundation was, as we've established, massive overkill for the stable bedrock it sits on. One theory is that it was for seismic resistance, as Baalbek is in an active earthquake zone. Seismic maps of the region confirm the risk. The idea is that the monolithic blocks would move as a single unit, surviving quakes that would topple smaller constructions. This is plausible, but it runs into the Roman contradiction. The Romans were brilliant engineers, but their solution to earthquakes was typically arches and flexible mortar, not brute force mass. This platform is anti-Roman in its design philosophy. So if the incentive was earthquake proofing, why did they choose a method so alien to their entire engineering tradition? What about the labor? The cost is not just in materials, it's in people. Quarrying, transporting, and placing these stones would require thousands of skilled and unskilled laborers working for decades. This demands a massive support infrastructure: housing, food, water, tools, and a rigid command structure. You can estimate the caloric needs, the toolware, the sheer logistics of keeping that many people productive in one location for so long. Where is the archaeological evidence for this massive, long-term work camp? A project of this scale leaves a huge footprint. Not just the monument itself, but the city of workers that built it. The evidence for such a logistical hub is thin compared to the scale of the work. You cannot cheat the basic needs of a workforce. Where did they all live, and what did they eat? Finally, on cost, we must consider the risk. Every stage of this process is fraught with catastrophic failure potential. A block could crack in the quarry, wasting years of effort. The transport system could fail, destroying the block and killing dozens of workers. The final placement could go wrong, damaging the adjacent stones and setting the project back immensely. With 800-ton loads, a single failure is an unrecoverable disaster. Modern project planners use risk assessment matrices to quantify these things. The risk level here would be off the charts. The incentive to find a simpler, safer, cheaper way, like, for instance, using the concrete the Romans had already perfected, would be overwhelming. Stop buying it. Why would any sane planner choose the single most expensive, most dangerous, and most difficult method imaginable to build a simple temple foundation on solid rock? Now, let's track the path of a single stone. This is where the official story truly breaks down. The source quarry is located about a half-mile away and at a slightly higher elevation. This suggests a downhill transport strategy, which makes sense. But the ground between the quarry and the temple site is not a smooth, prepared highway. It's uneven terrain. The first step would be to build a road capable of supporting not just the 800-ton block, but also the machinery used to move it. This road would need to be wide, incredibly stable, and have a consistent, gentle gradient. Surveying the route with modern equipment confirms the required earthworks would be a major construction project in itself, leaving traces that should be visible today. Where is this grand transport causeway? Let's talk about the method of transport. The common suggestion is that they used wooden rollers. Be honest, an 800-ton block would exert so much pressure that it would crush standard wooden rollers into pulp. You can calculate the ground pressure by dividing the weight by the contact area. To make it work, you would need an impossibly large number of rollers made of an incredibly dense, strong wood, all moving in perfect unison over a perfectly flat surface. The logistical complexity of managing thousands of rollers, constantly moving them from back to front, while keeping the massive stone perfectly balanced, is staggering. What breaks first? The rollers themselves? Or the ground beneath them? Or the coordination of the pulling teams? This entire explanation is a work of fiction. How is this a serious engineering proposal? Even if you solve the roller problem, how do you provide the motive force? How many people does it take to pull an 800-ton block, even on a slight downhill slope with rollers? The force needed to overcome inertia and friction is still enormous. We are talking about thousands of people, or a massive array of capstans and animal teams, all pulling in perfect synchronization. The organization required is mind-boggling. You'd need a command structure like an army, with signals and overseers, to ensure the force is applied evenly. One team pulling slightly harder than another could skew the block and cause a catastrophe. Again, this massive logistical effort should leave archaeological evidence. Anchoring points for the capstans, remains of the pulling mechanisms. The absence of this evidence is a critical flaw in the narrative. Reality does not care about your story. Where is the evidence of the engine that moved the stone? Then comes the final placement, the last logistical nightmare. You have gotten your 800-ton block to the construction site. Now you have to lift it several meters into the air and slot it precisely into the wall. As we've noted, the tight space prohibits large cranes. So, what's the alternative? Ramps. The theory is they built enormous earthen ramps and dragged the stones up. But a ramp to lift a stone to that height, with a shallow enough gradient to be usable, would be a colossal structure in its own right. It would contain more material and take more effort to build and remove than the temple itself. Calculating the volume of such a ramp shows it would fill the entire courtyard. And after placing the stone, you have to dismantle this mountain of earth and timber. Where did all that material go? There is no evidence of such a massive ramp, nor a place to dump the fill after its use. It's a solution that creates an even bigger problem. So if it wasn't cranes and it wasn't ramps, what was it? The entire logistical chain is nonsense. From the quarry to the wall, every single step presents a problem that is either unexplained or explained with a solution that is physically implausible or leaves no evidence. A practitioner knows you cannot just focus on one part of the job. The entire workflow has to be viable. Here, not a single link in the chain holds up to a basic constraint check. You can't just say they were geniuses and leave it at that. Genius still has to obey the laws of physics. So why does the official explanation require us to believe in one miracle after another? Let's move from the brute force to the fine work. The seamless fit of the Trilithon stones is a feat of pre-industrial manufacturing that defies easy explanation. How did they survey and mark the stones in the quarry to ensure they would match perfectly on site, a half-mile away? Today, we would use laser scanners and computer-aided design. They would have had plumb bobs, squares, and measuring cords. Achieving this level of precision over such large, irregular pieces of stone with such simple tools implies a methodology that is completely undocumented. Try this on a small scale. Take two rough rocks and try to shape them with hand tools to fit together perfectly. Now imagine doing that on the scale of an 800-ton block. The accumulation of small errors would be unavoidable. How did they eliminate all error? Think about the process of dressing the stone faces. After the block is quarried, its faces need to be made perfectly flat, or true. This is painstaking work done with chisels and hammers. To get a surface flat enough to create that knife blade tight fit, you need a reference. How did they create a perfectly flat reference plane over a surface area so large? A modern machine shop uses massive granite surface plates, themselves precision ground, as a reference. What was the ancient equivalent? The quarry shows evidence of how they split the blocks from the bedrock using channels and wedges. But the tools and techniques for achieving this final, superfine finish on such a massive scale are a complete mystery. You cannot cheat the laws of geometry. Without a reliable reference, how can you create a perfect plane? The challenge of precision extends to the assembly. The blocks in the foundation course had to be perfectly level before the Trilithon could be placed on top. If the foundation course was off by even a single degree, that error would be magnified in the upper courses, making a tight fit impossible. How did they achieve a perfectly level foundation over such a large area? Leveling a small building is one thing. Leveling a platform for 800-ton blocks is another. They would need incredibly precise water levels or other surveying tools, and a method for making micro-adjustments to the massive foundation stones. How do you nudge an 80-ton stone, let alone an 800-ton one, a few millimeters to the left to make it perfectly level? The tools and techniques required for this level of fine-tuning at this scale are simply not present in the historical or archaeological record. Where are the tools for that job? Furthermore, the entire platform had to be perfectly square. The corners had to be true right angles. Again, this is a basic surveying task that becomes exponentially harder with scale. The standard method of checking for square is the 3-4-5 triangle rule, which can be done with rope. But over the distances involved at Baalbek, rope stretches and sags, introducing errors. To maintain squareness over the entire megalithic enclosure would require a level of surveying accuracy that is, once again, extraordinary for the time. The slightest error in the foundation layout would mean that the last block in a sequence simply wouldn't fit. The precision is not just in the individual stones, it's in the entire system. Stop buying the easy answer. How did they maintain sub-millimeter accuracy over a construction site the size of a city block? Now consider the resources. Beyond money, what physical resources are required? The primary tool for quarrying and shaping stone was other, harder stone, and some metal tools like bronze or iron chisels. The wear and tear on these tools would be immense. To quarry and dress thousands of tons of limestone, you would need a constant supply of new, sharp tools. This implies a massive industrial operation running in parallel. Miners for the ore, smelters for the metal, blacksmiths to forge the tools, and a logistics chain to get them to the workers. Checking the archaeological record for evidence of this industrial-scale tool manufacturing shows very little. Where are the slag heaps, forges, and metal workshops on a scale commensurate with the Baalbek project? The resource footprint seems too small for the work accomplished. Where did they get their tools? Let's consider the wood. Whether for rollers, levers, scaffolding, or ramps, the amount of timber required would be staggering. We're talking about entire forests being cleared. the logs needed for rollers or massive levers would have to be from old-growth trees, straight-grained and free of defects. Where did this wood come from? Lebanon was famous for its cedars, but were they available in the quantity and quality needed? Pollen records and historical accounts used to reconstruct the ancient landscape show that a project of this scale would have a visible ecological impact. The demand for wood would have been a major bottleneck. You cannot build without materials. Where is the evidence of the deforestation and the massive timber processing industry that this project demanded? And then there's the human resource. It's not just about numbers, it's about skill. You need highly experienced quarry masters, stonemasons, surveyors, and engineers. These are not skills you learn overnight. This implies a guild or a tradition of megalithic building that was passed down through generations. But where are the other examples of this tradition? Baalbek seems to stand alone. While there are other megalithic sites, the scale and precision here are on another level. A skill base this advanced should have left other similar structures. The Great Pyramid, for example, was the culmination of a century of pyramid building practice. You can see the evolution of the techniques. Where is the practice for Baalbek? Where are the smaller, earlier attempts that show the builders honing their craft before tackling the 800-ton Trilithon? The organizational resource is perhaps the most critical. You need a leader or an engineering committee with a vision and a plan that can be sustained over decades, possibly centuries. This plan has to be communicated and executed flawlessly by thousands of people. It requires a stable society, a strong central government, and a continuity of purpose that can withstand wars, famines, and changes in leadership. The project itself, as evidenced by the abandoned stone in the quarry, was suddenly halted. This points to a failure in that organizational stability. But the part that was completed shows an almost superhuman level of planning and control. Reality does not care about your story. What kind of organization could maintain such perfect execution for so long, only to vanish so completely that they left no name, no record, and no explanation? Now, what are we not seeing? The first piece of hidden context is the orientation of the temple. The Roman Temple of Jupiter is not perfectly centered on the megalithic platform. It's slightly askew. An architect or a surveyor will tell you this is a bizarre detail. The Romans were obsessed with symmetry and order. If they had built the platform from scratch for their temple, they would have made it perfectly aligned. The off-center placement, visible on any site plan, strongly suggests they were adapting their plan to a pre-existing structure they found. The simplest explanation for the misalignment is that the platform was already there. Why would they build their own foundation and then fail to center their main building on it? Another critical piece of context is the erosion. The large foundation stones show significantly more advanced weathering patterns from wind and rain than the Roman ruins sitting directly on top of them. A geological analysis of the differential weathering of the stones confirms it. Different layers of stone, exposed to the same climate for different lengths of time, will show different levels of erosion. The fact that the lower megalithic stones appear much older than the Roman stones above them is direct physical evidence that they do not share the same construction date. The foundation was sitting there, exposed to the elements, for a very long time before the Romans ever arrived. How does the official story account for the foundation aging faster than the building it supposedly supports? The function of the Trilithon is also hidden context. It's not a decorative facade. It sits in the outer west wall, where the ground falls away. The Trilithon and the other megaliths in this wall are part of a massive retaining wall designed to hold back tons of earth and fill. This is structural, not aesthetic. But it also means the most incredible engineering feat on the site was mostly hidden. Look, the builders put their greatest effort into the part of the structure that was doing the hardest work, not the part that was most visible. This is a purely functional decision. It reinforces the idea that the platform is a drastic, overkill solution to a massive stability problem. But what problem? The bedrock itself is stable. So what was the platform built to stabilize? The final piece of hidden context is the unfinished nature of the site. On the north and south sides, the megalithic enclosure stops abruptly. The massive construction campaign was clearly abandoned mid-process. This is not a finished, complete structure. It's a project that was interrupted. This, combined with the abandoned 1,650-ton block in the quarry, paints a picture of a sudden, catastrophic end. The official narrative of a planned Roman construction doesn't fit this evidence. Roman projects were typically seen through to completion, or at least to a state that looked finished. This looks like a construction site where the workers dropped their tools and fled. Stop buying it. If this was a continuous Roman project, why does it have a clear, unfinished boundary, as if one building era ended and another, completely different one, began on top of it? Now let's analyze the failure modes. In any complex engineering project, you think about what could go wrong. What breaks first? With 800-ton blocks, the answer is everything. Imagine you've spent 5 years quarrying and dressing a single Trilithon stone. During the move, it develops a hairline fracture from the stress. The entire block is now useless. The project is set back 5 years. A system that relies on single, irreplaceable components is incredibly fragile. The builders must have had either a way to guarantee the stones would not crack, or they were willing to accept a failure rate that would make any modern engineer refuse the job. How did they manage this risk? Consider the transport system again. If it's rollers, a single broken roller could cause the entire load to shift, potentially toppling the stone. The resulting accident would be unimaginable. If it's a sled, a failure in the track could cause the block to become immovably stuck. How do you recover from that? How do you jack up an 800-ton block in the middle of a field to repair the track underneath it? A project plan without a contingency for failure is just a wish list. The sheer number of potential catastrophic failure points in the quarry to placement chain is terrifying. You cannot cheat risk. What systems did they have in place to mitigate these constant deadly threats? What about a failure during the final lift? Imagine the block is being hoisted or dragged up a ramp. A rope snaps, a winch fails. The block slides back, destroying the ramp, the tools, and anyone in its path. The kinetic energy of an 800-ton object, even moving slowly, is immense. The safety protocols for such an operation would have to be incredibly strict. But again, we see no evidence of them. We see no evidence of the massive anchoring points needed for safety lines, or the kind of redundant systems you'd need to prevent a runaway block. The entire operation seems to have been performed with a confidence that borders on reckless, unless they possessed a technology or technique that made it fundamentally safe. What was that technique? The most subtle failure mode is a failure of measurement. Let's say the foundation is laid out, and the first Trilithon block is placed. Then the second. As you bring the third and final block, you discover a cumulative error in your measurements. The gap is 2 centimeters too small. What do? You cannot trim the 800-ton block on site. You cannot nudge the other 2 800-ton blocks apart. The entire project grinds to a halt because of a tiny measurement error made months or years earlier. This zero-tolerance approach to construction is another sign of a methodology so advanced and so confident that it feels out of place. Be honest. Does this sound like the work of engineers who used rope and bronze, or does it sound like something else entirely? Finally, every engineering decision is a trade-off between cost, time, and quality. The builders of the Baalbek. Platforms seem to have ignored this rule. They chose a method that maximized cost and time to achieve a level of quality and durability that was absurdly unnecessary. Why? What were they trading for? Why choose solid, 800-ton monoliths over smaller, more manageable blocks? One clear advantage is that fewer joints mean fewer points of failure. A wall made of huge blocks has fewer pathways for water to seep in, and it's less likely to have its internal fill leak out. It creates a more stable, monolithic structure. So, they traded immense upfront difficulty for extreme long-term stability. But this trade-off doesn't make sense in the context of the Romans. The Romans had already solved this problem with their invention of waterproof concrete. They could build massive, stable, monolithic structures quickly and cheaply by pouring concrete into forms. It was their signature technology, visible in the Pantheon, in their aqueducts, in their amphitheaters. They could have built the entire Baalbek platform out of concrete for a fraction of the cost and effort, and in a fraction of the time. The choice to use megalithic stone instead of concrete is a direct rejection of their own superior technology. This is perhaps the most damning piece of evidence against the official narrative. Why would the world's experts in concrete suddenly decide to imitate Bronze Age builders and take on the most difficult stonework project in human history? Let's consider the seismic angle again. Is it possible that even Roman concrete wasn't trusted to withstand the earthquakes in that specific valley? Perhaps they knew something about the local geology that demanded this extreme solution. This is a possible trade-off. They sacrificed efficiency for what they believed was the only way to guarantee the temple would last for millennia. But if that were the case, why is this technique not used in other Roman temples in other earthquake zones? Baalbek remains a unique anomaly in the Roman world. If they had developed this super earthquake-proof building style, it would have been a massive engineering breakthrough, and they would have deployed it elsewhere. The fact that they did not suggests this was not their invention. Reality does not care about your story. A revolutionary technology is either used again, or it wasn't yours to begin with. So the trade-off remains inexplicable. The builders chose the most difficult, expensive, and time-consuming path possible. They sacrificed everything for a level of precision and mass that served no clear, practical purpose for the temple that was eventually built there. It's a solution in search of a problem. The sheer irrationality of the engineering choice, especially for the hyper-rational Romans, is what fuels the core of this mystery. You cannot simply ignore the fundamental character of the supposed builders. The Trilithon is not just an engineering marvel, it's an engineering statement that is profoundly, fundamentally anti-Roman. How can both be true? Now we must explicitly address the alternative hypothesis. The constraints, the costs, the logistics, the lack of records, the contradictory engineering philosophy, they all point away from the Romans as the originators of this platform. The alternative hypothesis is simple. The Romans did not build the megalithic foundation. They found it. They arrived at Baalbek and discovered a massive, ancient, and possibly ruined platform of incomprehensible scale. It was flat, it was stable, and it was perfectly situated. Being practical engineers, they did what any practical engineer would do. They reused it. They built their temple on top of this ancient foundation because it saved them the immense work of building their own. This hypothesis resolves nearly all the contradictions. It explains why the Roman temple is off-center. They were adapting to a pre-existing layout. It explains the different erosion patterns. The foundation is much older because it is. It explains the lack of Roman records for the construction. They didn't build it, so there was nothing to record. They documented their own temple construction, but not the foundation, because it was not their work. It explains the alien engineering style. It was not Roman engineering. It was the work of an earlier, unknown culture with a completely different set of tools, priorities, and techniques. This explanation is simpler, and it fits the physical evidence far better. So why is it not the official story? It also explains the unfinished nature of the site and the abandoned stone in the quarry. The original builders, whoever they were forced to abandon their colossal project. Generations, perhaps centuries later, the Romans arrived, found the abandoned site, and built their own temple on the most complete section, the western platform. This hypothesis treats the platform not as the beginning of the Roman temple project, but as the end of a much older, much more ambitious one. The megalithic structure is not a foundation for a temple. It is a ruin in its own right. The Romans were just the last in a long line of people to use the site. The site contains two stories, not one. Why are we so committed to forcing them together? This alternative view reframes the entire mystery. The question is no longer, how did the Romans move these stones, but who were the original builders, and what technology did they use? It acknowledges the stark difference in scale and style between the platform and the temple. Look at the site. There are two distinct architectural signatures present, one of graceful Roman columns and carefully carved decorations, and another of brutal, incomprehensible mass and precision. To claim they are both the work of the same people, at the same time, requires ignoring the most obvious physical evidence. You can verify the stylistic clash with your own eyes. The two parts of the site do not belong together. Why do we pretend they do? So, here is the verdict. The official story that Roman engineers quarried, transported, and placed the 800-ton Trilithon blocks is insufficient. It fails to survive contact with nearly every real-world constraint we can apply to it. It is contradicted by the lack of historical records, by the alien engineering philosophy, by the physical evidence of differential weathering, and by the sheer logistical and economic absurdity of the choice. The narrative requires us to believe that the most practical engineers in history chose the least practical method, in total secrecy, to solve a problem that didn't exist. This is not a plausible explanation. It is a story of convenience that papers over a profound and disturbing mystery. It is a forgery. The evidence strongly suggests that the megalithic platform at Baalbek predates the Roman temple. The Romans were not the builders. They were the inheritors. They found a platform of the gods and built their own temple on it, a testament to their own ambition, but a pale shadow of the engineering feat that lies beneath their feet. The real mystery of Baalbek is not the Roman temple. The foundation is the real wonder. The identity of its builders, the source of their technology, and the reason for their sudden disappearance remain completely unknown. The Trilithon is not a Roman achievement. It is a legacy, a message in stone from a lost chapter of human history. The story is not closed. The evidence is right there, in the mismatched stones and the silent, impossible blocks. The official explanation is nonsense. The real work of solving this puzzle has barely begun. If you want more forensic breakdowns that challenge official stories by applying real-world constraints, subscribe for the next investigation.